My name is Nardos Ashenafi. I'm a doctoral candidate here at Boise State University in the electrical engineering department. And I work in the robot control laboratory, which I'll talk about a little bit down the road. But a little bit of background behind me. I was born and raised in Ethiopia. I came here for college to Boise, Idaho. That's a different story there. And now I'm continuing my graduate school, and hopefully I will graduate in 1 year. And what I will do today is I'll actually share some content about my thesis with you and actually give you a little bit of background about what we do in the robot control laboratory as well. So a lot of people don't know this. But there is a robotics lab on main campus BSU. It's on the first floor of the MEC building, the Micron Engineering Center. So a little bit of e-tour, since a lot of people don't know it. So when you walk right into the lab, the first thing everybody notices is the air hockey table that is sitting in the middle of the room. No, we're not spending time playing hockey instead of playing air hockey instead of doing our work. But this is actually a robotics project we did a couple years back. It's a senior design project. And as you can see, we have some robotic mechanism on one side, and then you have a player on the other end. And we have our camera, which looks at our pug, tries to make the prediction, tries to predict the position and velocity of the pug at some time. And this mechanism, when you look at a top-down view of it, is this what we call a pantograph mechanism. And it has two motors on the ends, and the striker is attached. And when you move the two motors, you'll be able to actuate the striker. So you're thinking it, so I'm going to answer it. Yes, it played well. It was a very interesting project. And can you defeat it? Everybody asks that. Yes, you can. You can definitely defeat it. But it was a very interesting problem. And we also have these serial robots in the lab. And I want to take this opportunity to tell people about a robotics class that's offered here at BSU. We actually have an introductory class taught by my advisor, Dr. Satichi. And this, in the class, we teach people about forward and inverse kinematics. So if I tell you where I want the end effector or the tool to go, can you tell me what the joint angle should be and what the joint velocity should be? So if you're interested, it's offered for mechanical and electrical engineers and computer science students as well. But mostly we have a bunch of small mechanisms on which we test our control algorithms. And we have a bunch of pendulum, but I will explain to you why we're interested in them. So this is called a Fruta pendulum. And in action, it looks something like this. This was just a fun video we took in the middle of our run. So it was a senior design project, and it's just really entertaining to actually see one of these working. So what is happening is we're trying to do the swing up task. We're trying to stabilize this pendulum at an upright, and you have an axis. There's actually a shaft going right through, and there's a motor at the bottom, and the motor is turning that vertical axis. But this link is free to rotate. It doesn't have any motor on it. So you have to be systematic on how you swing, and you could do some pretty interesting maneuvers in order to swing it to the upright. And so we're interested in these, what we call underactuated systems, and I'll explain to you what they are and why we're interested in them. And another thing we do, actually a lot of our work is in simulation, and we verify them with experiments, but this is a multi-agent problem we did a couple years back. So you have a polygonal object, which is imagined as a box in a warehouse. And you have 4 mobile robots, and you're trying to manipulate this robot by trapping it. You're trying to trap the box and transport it, right? And you can translate it, you can rotate it. And this was a very interesting project we did a couple years back. This problem is particularly interesting and difficult because you cannot use friction along the sides of the box to transport it. You actually have to entrap it, apply normal contact forces, and do the maneuver. So as you can see, we're interested in control design, right? So a lot of the theme that you see, whether it be the Fruta pendulum or in fact the multi-agent system that I showed you, we are interested in underactuated systems. So what are underactuated systems? Well, let's take this another example of a pendulum. This is a double pendulum. You have 2 joints, the yellow dots that you see, and you don't have control over both of those degrees of freedom. So imagine like this is your arm, you have the elbow and the shoulder, but you cannot actuate both of them because you don't have a motor on both. You only have a motor on one, and you want to be able to swing this to the upright. And this is an underactuated system because you don't have control over all your degrees of freedom. If you want to create some acceleration in arbitrary direction, you don't have enough control authority or enough motors to do this arbitrary motions, right? So that is an underactuated system. And another example of that is actually a drone. A drone has 6 degrees of freedom, right? It can move forward and back, up and down, it can rotate, but it only has 4 propellers, and your 4 propellers are capable of translating up and down instantaneously. But if you've noticed, if you actually want to move forward, you have to tilt forward and then you have to go, right? So you cannot have an acceleration forward and back instantaneously. So that's an example of an underactuated system. So they're more common than we realize. And we're interested in them because, one, they're efficient. You don't have motors on every joint, just like the devil's pendulum or the acrobat that we saw. Or you have limited torque available to you. So you have torque limited manipulators all the time. So you need to be smart about how you control such systems. And we are interested in those systems. We're interested in designing control algorithms for those systems. So another good example is actually a simple pendulum. You just have a joint right here. You have a motor on this joint, so you can actuate it, and you have your mass concentrated on the end. And you can actuate this guy with a limited torque. So you have degree of freedom, you can control this degree of freedom, but you don't have enough control authority. And we're interested in this because it's actually a nice model for walking robots. It's a simpler model of walking robot. If you look at an inverted pendulum, it looks like a robot that is pinned about the ground that is in contact with, and its hip is where the mass is concentrated, right? So we're interested in the swing up tasks of pendulum, and I'll talk about that over and over again. So slowly coming into what we're going to be talking about today. So how do you control such underactuated systems? Well, there are many ways, but I put them into 2 categories for this discussion. I put it under classical control and data-driven techniques. So in classical control, typically what we do is we write the dynamics out. We see how we can manipulate the controller such that we can achieve whatever task we want to achieve, whatever performance we want to achieve. So there's a lot of writing the equations, manipulating the equations, and whatnot. So it's system specific. You need to have what kind of dynamics you have on your hand. But the beauty of such classical control methods is you can say something about the stability of the system. You can tell me, hey, it's going to, for all the state space or for a portion of the state space, it will actually go to the stable equilibrium, or it will converge in this nature. You can tell me a lot about the system. On the other hand, there are data-driven techniques, or nowadays what we call machine learning techniques. And such methods are actually much nicer because you don't have to manipulate the dynamics like you do with classical control. You could perform repeated interaction with the system, see what observations you get, what rewards you accumulate, and try to infer what controller does the performance that you want. So it's flexible across your systems. You don't have to be bound to a certain class of dynamics. You can make it work for a large class of systems, but it lacks stability certificates. So just like the classical control, I cannot always guarantee you for majority, not all, but majority of data-driven techniques, I cannot tell you the stability of the system easily. So a good example of data-driven technique is reinforcement learning. And I took this from OpenAI Jim's site. It's a team that has been designing environments. So they have a lot of dynamics available for people to use, and they have reinforcement learning algorithms that they've implemented as well. So they taught a robot, such as this one, how to walk. So they start with a random policy, they act upon that policy or controller, and then they see how the dynamics performs, they accumulate a reward, and they try to update their controller based on those observations. So this is an example of a data-driven technique. So the overall training process looks like this. It's a constant interaction with the system. Send an action, get an observation, send an action, get an observation, until you converge onto an optimal policy. So while this talk of machine learning is really great and reinforcement learning is pretty powerful, does that mean we're going to toss out this classical control stuff? And the answer should be no. We should not be forgetting all this insight we've been gaining from classical control. In particular, we have been able to say a lot about stability of a system from classical control, so we should actually incorporate that into our machine learning techniques. And if you think about it, the data-driven technique and the classical control actually complement each other. So if you have a classical control technique injected onto a data-driven technique, it will give you insights about stability. But on the other hand, if you have difficulties that you've been facing in classical control, you can actually solve them using machine learning techniques. Okay, so we're going to find this healthy balance between the two. And you may be thinking, okay, what classical control are you talking about? Well, I'm going to take a particular example. I'm going to take a mechanism called passivity-based control and see how data-driven techniques can be injected onto that. So I'm going to just define two concepts to explain how passivity-based control works. And once we have the basic understanding of it, we can talk about the machine learning part. So how does passivity-based control work? Well, first, we're interested in systems that are called dissipative. Sorry, I can't say that word correctly. Bear with me. So dissipative systems are defined by some, dissipative systems have a storage function, or what we call the Hamiltonian, that have the following properties. So the Hamiltonian at time t1 is less than the Hamiltonian you had initially at time t0, plus the input or the supply rate into the system. So what does that mean? Well, this Hamiltonian, you can think of it as the energy of the system. And in fact, for mechanical systems and the robotic systems, it's the total energy of the system. So this is saying, imagine the energy you had at the beginning at time t0, and imagine the energy you're inputting to the system. That is always equal to or less than the energy you have at time t1. So the system is dissipating energy, or it doesn't have any internal energy generation. So that's what we're showing here. And even more interesting, if I actually take out that input into the system and I just look at the energy, if it obeys this inequality, then my Hamiltonian or my energy is decreasing, right? So I'm interested in systems that have decreasing H value. And I'll explain that in a little bit why I'm interested in that. And then the second concept I want to introduce is passivity on top of a dissipative system. Imagine the right-hand side we would look at, the S value under that integral has a particular form. It's the form U transpose Y, where U is the input into your system. So let's say the torque applied by your motor, and Y is the output. Let's say the velocity that you end up with. So if the S value is of the dot product between your output and your input, and this inequality still holds, then the system is called passive. And you can put even stricter conditions onto it. You can say, okay, on top of the dot product between the input and the output, I have some positive delta value, and then the magnitude of the output, and that inequality still holds, is output strictly passive, and then the same thing for the input to define the input strictly passive. So why am I interested in systems that are dissipative and particularly that are passive? Well, if I can find a system whose energy is positive everywhere, bigger than or equal to 0, but the rate of change of that Hamiltonian is less than or equal to the dot product between my input and my output, the system is passive, but it's also stable. So as time goes on, I will actually converge to the value of x equals 0. This is very important. So you're not limited to x equals 0. You can think of other stable equilibrium that you're interested in. You can just shift your point of interest. So to give you physical interpretation, if you have a walking robot and you want it to converge to a motion where it has a constant speed of 2 meters per second, you can actually have it converge 2 meters per second. If you can prove to me that your controller has this H value, your controller creates a system that has this H value and this H dot property. Okay? So we just want, in the end, we want to result in a system that has a Hamiltonian of this form that I can guarantee the stability. So here's how we extract controllers from such systems. So take the simple pendulum. So in the case of the simple pendulum, we're interested in the following. So your pendulum naturally, hangs in the stable equilibrium, which is the downward equilibrium, and that is a Q equals 0. Q is the angle, and we want to swing it up to the upright. And when you do that, you're just fighting the natural dynamics, right? So it doesn't naturally go to that unstable equilibrium. So here's what we want to do. The dynamics of the pendulum looks as follows, where H is the energy of the system, nothing but the sum of the kinetic and the potential energy, right? But what I want to do is I actually want to transform my dynamics from this form to this form. And the difference is now my new system has a new Hamiltonian H sub D. And interestingly, this H sub D is designed such that its stable equilibrium is where I want it to be. I want it to be now in the upright. Okay, so I'm literally transforming, or what we call energy shaping. I'm changing the energy of the system from H to H sub D by applying this control. So the question is, what is this control that turns my dynamics from this form to this form? And you can extract it out. And it's given to you right here. So you literally want to set this equality to this equation, and find the controller that the sets these two equal. So we have two parts to the controller. We have the energy shaping part. So it turns our system from having Hamiltonian H to having Hamiltonian H sub D. And then we have some damping terms. So the damping term allows you to asymptotically go to your equilibrium point Q star. So the question is, what is this HD? Because if you tell me what HD you want, what energy you want in the end, I can in fact tell you what controller takes you to that H sub D. So that's the mystery. How do you find that H sub D? So in the case of the simple pendulum, it's simple enough that I can actually tell you what the resulting energy should be such that the stable equilibrium is upright, and it's given as follows. You have the kinetic energy as well, and it's minimum when the velocity is 0. But the potential energy term is 0 when you reach Q star, where Q star is at pi, the upright. So I'm giving this, I'm telling you this because the pendulum is a simple system. And given that you have this quadratic expression, you can actually find the derivative and prove that HD dot is less than or equal to 0 and has the form Y transpose U. And from this, we can say what the controller is because we can extract it from this equation, as long as I know what HD is. So this is the controller that will actually swing your pendulum and make it go to the upright. So as long as you pick these gains, your KP and your KD, then you will be able to find a controller. So while the pendulum is really nice and it's so easy to tell what HD you want, when you have complicated systems, it's difficult. This is the Bolbot, and there is a paper that actually tries to find an energy shaping control or a passivity-based control. And it's a rather complicated system. So you have a wheel on the bottom, a spherical wheel on the bottom, and you have a rather long body, right? And it's really an interesting stabilizing problem. So it takes a lot of writing out the equation of motion and then finding what that H sub D is. And the way you find that H sub D is actually by solving a partial differential equation, this partial differential equation. And it's rather difficult when you have a complicated system. So here is the beauty of having to inject machine learning techniques on an already existing passivity-based control. Well, that PDE is very difficult to solve for complicated systems, but what if I can actually solve it with data-driven techniques, right? So instead of solving that HD from a partial differential equation, I can approximate it with a neural network. And I can actually approximate that neural network, what that H sub D is, through repeated interaction with the system. So a little bit of a combination of the two. And the beauty of it is, if I can find that H sub D, I can actually still do the stability certificate that I've been doing under the classical control technique. So we still have the good stuff from classical control. We have the stability that is intrinsic to our model. And we have other more important, interesting concepts we can add due to data-driven techniques. We can account for model uncertainties, and I'll talk about that a little down the road. And if you have a new system, you don't have to constantly, manipulate your dynamics like we did for the Bolbot. You can plug and unplug just like how you do for reinforcement learning. So the data-driven passivity-based control form, we call it NEURALPBC. And it's what we've seen before, but a little bit of summary. So you have the dynamics of your system. It has a Hamiltonian H, and you want to find this controller such that it obeys this form. And this comes directly from the passivity-based control we saw for the pendulum. And the task is to find HD, but now I'm going to approximate HD with a neural network. So this theta is the parameters of the neural network. And we're going to actually find that HD such that our stable equilibrium is X star. And we want our controller to take us to the neighborhood of X star. So we can pose that problem as an optimization problem. We have the dynamics, we're operating under these constraints. We have a controller, which comes from passivity-based control, but we have a loss function. And that loss function holds the information as to where our stable equilibrium is. So we'll tell it, okay, if you're closer to the desired equilibrium X star, then here's the cost you accumulate. If you're further away from it, you accumulate a lot more cost, but our objective is to minimize it. So eventually that loss should minimize and we should go to our stable equilibrium, to our desired equilibrium. So there are three important tasks that we need to do in order to achieve this. Well, first we need to design that loss function well. We need to be smart about how we design our loss function. Second of all, how do we take the gradient of that loss with respect to the control parameters theta? Because we want to update theta following the gradient of that loss. And third, we want to be able to sample our state space efficiently because we need to generate data. But when you generate data, you don't want to be wandering around all your state space. How can you be efficient about which part of the state space you're going to learn over? So the loss function, we typically use what we call side distance loss and transverse loss. So to compute this loss, you take your controller, the parameters that you started with, let's say random controller, you generate a trajectory, and then you compute the loss accumulated by that trajectory, and then you update based on the gradient of that loss with respect to the parameters. So there is a small interesting thing going on because we're going to take gradients through the differential equation that generates the trajectory. So set distance loss is nothing but you have an equilibrium that you're interested in, and you want to go somewhere close to the neighborhood. I want to be closer to the neighborhood of that stable equilibrium. So what I'm going to do is I'll say, okay, if you, during this trajectory, if at any point in this trajectory, if you reach within this stable equilibrium, the equilibrium that I'm interested in, then I will give you no cost. Okay, so that will encourage your states to be drawn towards the point that you're interested in. And if you don't reach this point at all, if you're wandering around, if you're here or if you're there, then you will be given some cost. You'll accumulate. So if you're wondering what happens once I reach the neighborhood of X star, well, we have techniques such as linear quadratic regulator that we can use to catch it, right? If you're close enough, we have some pretty good methods to keep it there, but the problem is actually having to get to that equilibrium. So this plot that you're looking at is that of a pendulum. This is the pendulum angle, and this is the pendulum velocity. And the pendulum, this is it swinging and then going to the upright. But another thing you could do is if you have a system whose path you know, for example, let's say you have a walking robot and you already know what path you want it to follow, but you just want a controller that tracks that path, you can actually compute the loss that says, okay, here's a controller, generate trajectory. How far is my trajectory from the path that I want? And then punish that accordingly. So that is what we call transverse distance loss. You can also punish the amount of control it takes to do it, because after all, we're still in the underactuated realm. We have limited torque. Okay, so the state sampling. So we said we generate a trajectory. We need to start from some initial state in order to generate that trajectory. But how do we pick the initial state? Do I just randomly wander around for all the state space and try to learn every single point, which you can't because you're in the continuous realm? So we have this concept called dagger, and this actually comes from imitation learning. I remember seeing this explanation on one of the reinforcement learning videos, and I think it explains how and why dagger works well. So imagine you're trying to teach an autonomous vehicle how to drive, right? So you're driving along a straight line and imitation learning. So you're trying to have it mimic you when it perceives the same environment you're seeing right now. So you have your cameras, you see a straight line, so you drive along a straight line. The next time it sees that world, you want it to do the same thing. You reach an intersection, you want it to turn, right? But if you just try to drive randomly and you try to make it take as much information from you as possible, it doesn't do a good job. The better thing to do is actually to have it in a certain scenario, see what trajectory it generates. Let's say it is very prone to making a right turn, right? Then what you will do is you will say, okay, first let's fix the issue that you have along the state. So I'm going to keep sampling along the trajectories, along the states it keeps visiting. I'm going to fix it, right? I'm going to constantly sample from that state and I'll say, okay, let me first take these states towards my equilibrium. And then now when it reaches another state space, I will refine that, I will fix the error, and then I will do refinement. So that is better than having to constantly wander around, and eventually you will actually be able to do a good job for a lot of your state space, right? You just don't want to perform well for one state, but for a bunch of them. So you want your loss to be minimum over the expectation of your X naughts, all your initial states. So taking the pendulum again, so this is what dagger looks like. You have the pendulum angle and then the pendulum velocity. And these are the equilibrium that we want to go to. 0 is down, but we actually want to go to pi or negative pi. That's the outward. And these lines, the dotted lines, are actually the what we call the homoclinic orbit. So that's pretty much your pendulum going back and forth until it reaches the stable equilibrium, the desired equilibrium, right? So we want, for wherever we start here, we want it to go to this guy. So what we're going to do is we'll say, okay, I start to send some random parameters. What states do you visit? So initially I don't do so well, right? All this is doing is it's just hanging down and trying to swing around the 0. So I'll say, okay, seems like you're interested in those states. I will sample a couple of states. I'll remember those blue dots. Let me generate another trajectory from another X naught. Okay, it looks like you're interested at this point. So I'll sample a couple here. And then a couple more. It seems like if I start here, these are the states you're interested in. So there's no point for me to, sample somewhere way out here. It looks like my controller is hovering around here. We need to fix the errors that are occurring. But we also do this technique where we sample a couple of states around the goal, right? Because if it starts here, I don't want it to explode. I want it to go to the equilibrium that I'm interested in. So I sample a couple of states here. So you do a combination of those two. And then from those X naughts, you put them together, you put it in a bucket, and now you start generating trajectories. So I generate a trajectory. Now I'm going to compute a loss based on that trajectory. So those purple ones contribute to my L. So I generate a couple more, and then I keep refining my controller accordingly. So this is what the training looks like, right? I have my initial states that comes from Dagger, or if I have a path planner, I can take states from my path planner as well, because I'm interested in those states. I put it in what we call replay buffer, which is pretty much a bucket. And then I sample some X naughts, I generate a trajectory, and this is solving a differential equation. And then I compute the loss, and I will take the gradient of that loss with respect to the parameter theta that generated the trajectory. And you do this over and over and over again until your loss L vanishes, right? It becomes minimum. So I said something that I hope raises a question to you. I said, I integrate this differential equation, I generate a trajectory, and then I compute a loss over that trajectory. But how am I taking that gradient? Well, there are techniques that exist, such as automatic differentiation. But the problem is if you take a differential equation that you solved iteratively and you try to take gradient through automatic differentiation, it's actually very inefficient. And you mainly want to do reverse mode and not forward mode in this case, because you have more inputs than you do outputs. So automatic differentiation is good, but it's not efficient. There are other techniques called adjoint sensitivity. And this is actually a technique designed to take gradient of some objective function with respect to a controller through a differential equation. But we have these f being the differential equation. We have to take the gradient of the differential equation with respect to x. And now we have neural networks injected in there. It's complicated, right? So adjoint sensitivity on its own does not know how to handle that del f del x. But you combine the two, it works beautifully. Because you can solve the gradient through this differential equation easily. And then at the same time, from the adjoint technique, and at the same time, you can take the gradient of f with respect to x through automatic differentiation. So the combination of the two is great. So the way we're doing this is we're using a package called diffq flux. We program with Julia, and that is a package available through Julia. Programming language called Julia. And to give you, this is from their website, from the page for the package, and they did a very simple fitting problem. So they have a differential equation, x dot equals f of x. They generate trajectory, and they say, okay, I actually want this trajectory, which is given by the red one, which is whatever I'm predicting right now. I want it to look like the blue one. And I want to tune the parameters of the differential equation such that this data fits. So they take gradient through the differential equation. This is also straight from their website, but they have this really nice example. So if you're interested in how you could learn parameters of your differential equation through machine learning techniques, or how you can take gradients of them through adjoint sensitivity and auto diff, I highly recommend it. Okay, so this was tested on the inertia wheel pendulum. So this is one of the many pendulum we have. So we have this link. This is our first link. When you forget this part, it looks like just a pendulum, right? But the difference is you have a motor that's actuating this wheel. So you have a belt drive here. As the motor turns, this wheel turns. And what we're trying to do is we're trying to use the momentum from the wheel to swing this thing onto the upright. And this was one of the runs we did. We didn't think, I was just recording, and it happened. Like we were just recording. We were like, okay, let's just do multiple tries. And this is one of the videos that I found. But I really like this video because the first thing you notice is that it looks like the swing doesn't look natural, right? It doesn't look natural because we overrode the dynamics. We gave it a new H.D, right? Now it does the performance objective we asked it to. It says we told it go to the upward equilibrium, which it does. It goes to stabilize it. But after this run, we said, okay, it looks like the wheel is turning really fast. How can we fix it? So what we did is we said, okay, on our performance objective, we need to be able to punish the speed of the wheel. And that's what we did. When you punch the speed of the wheel, it actually does this thing where it goes back and forth, really like back, forth, instead of spinning really fast, and still does the swing up task. And then when it reaches the upright, we catch it through LQR, linear quadratic regulator. So this opened up a very beautiful avenue because we still have this dynamics we have to deal with. We still have to write the equation of motion because we learn through simulation, but we always have this problem where we have uncertainty in our model. But the beauty is now we can inject our uncertainty into our learning, right? We can say, okay, I have data-driven techniques, I can do something about it. So what we did is, instead of using neural network to approximate the H, the Hamiltonian, we use Bayesian neural networks. And the difference between the two is that the weights and biases are not just point estimates, they're probability distributions. And you can in fact learn the probability distribution over the parameters. So what is the motivation behind this? Well, take a very simple system, a linear dynamical system. You have your parameter P, which is your mass of the system or the length of your pendulum or the combination of those two. So simple system, the parameter is P, and our controller is U. And we have the controller, which is simple, linear in state, so theta times x. So this is our system x of t given by an exponential, and we want to minimize this cost, this quadratic cost. So we want this x to die down to 0, and we want to use a minimum control. But let's say that parameter P is not exactly known to us. We have some uncertainty in our mass, we have some uncertainty in the length, or some other parameters like inertia. We just have an idea of how uncertain we are, so we can represent with this distribution. So we said, okay, let's compare what happens when we just assume we can learn one deterministic solution versus a probability distribution. So a little bit of calculation required in the background, but to take it to the answer, here's the deterministic controller that minimizes that cost, that theta star, that minimizes the j, and the distribution f of theta that minimizes the j. And when you plot these, it looks like this. So this is the probabilistic solution. This red arrow represents where theta star the deterministic solution is. And we have the expectation over the probability distribution is given by the black arrow. So the first thing I want you to notice is that this red arrow is not informed about the uncertainty in your parameter. And you're just assuming and hoping to God that you have the correct parameter and blindly using that parameter when really you could be anywhere in this distribution. So you have quite a bit of uncertainty and you're not taking that variance into consideration. So remember that plot, I'll come back to it. On top of that, you can actually have measurement uncertainties, which are more common than you think. If you have an encoder or a sensor, you have sensor noise and encoder noise, right? Therefore, when you incorporate that into the search for an optimal controller parameter, it looks like the following. So let's represent that measurement noise with some normal distribution. And now our differential equation becomes a stochastic differential equation. And now we have some noise process to represent the measurement uncertainties. And you can solve this differential equation, the stochastic differential equation as such. And we're interested in finding out, okay, what is the cost accumulated under the parameter uncertainty and under the measurement noise? And when you plot it, it looks something like this. So this is the uncertainty in your measurement. This is the uncertainty in your parameter. These are your controller parameters, your theta star for every variation. And this is the cost accumulated under the uncertainties. So look how much of a difference it makes. If you jump from, let's say, I have 0.4 uncertainty in my measurement, and I have, let's say, one uncertainty in my parameters, 5.39. But if I change it, if I change a little bit, you see how much my theta star changes? And this is important. It's important to know how much my controller changes, and then how much it actually changes my accumulated cost. And my accumulated cost changes quite a bit. So it is important to know how much of uncertainty you have, and having that uncertainty into your consideration makes the difference. So we proved it to ourselves. So we said, okay, let's take an example. Let's take the energy shaping problem we saw earlier, and we want to learn the swing up task. The deterministic solution is the one we did earlier. We said, okay, take H sub D we had found earlier. That is our deterministic solution. But now we want to learn a probability distribution over HD. And I'll explain how we found that HD, the probability distributions. And we plotted the following. So this is your parameter of the pendulum. There's only one system parameter. And this is the J, the performance objective, the cost accumulated. So lower is better. And what we saw is that, okay, I assume that I know my system parameter. I took measurements, and I'm guessing that my system parameter for the pendulum is about 9.8. But if I'm wrong, and if I deviate from this to, let's say, 10 point, whatever this is, like 10, 10.2, 10.3, my deterministic solution, having only 1 point estimate, starts to accumulate a lot more cost. And it gets worse. And the bottom two are stochastic solutions. And they seem to be very robust against my uncertainties. The band here represents my measurement uncertainties. And the blue line represents the marginalized. So I took a bunch of samples from the probability distribution and I marginalized it. So I took the average over those samples versus I took the maximum posterior, which is just, it takes the maximum over the probability distributions of the parameter. And this is under measurement noise that's very typical on an encoder, right? So we want our system to be robust, and data-driven techniques allow us to do that. So the way we find those probability distributions is straight from Bayesian theorem. We're mainly interested in finding the probability of theta given the loss, and that is equal to the likelihood times the prior divided by the evidence. So we can compute the likelihood. We can in fact design the likelihood because that L is the loss function. It's our loss function. We want to minimize it. And the prior is, you can either say, okay, I have no idea what this parameter should be, so I'll make it a uniform distribution, or you can say, I have an idea, I had a deterministic training. But that evidence is difficult to compute. It's intractable, in fact. Therefore, you can do an approximation called variational inference, where you pick a form for this P of theta. So let's say I pick a normal distribution, and I learn Z, where Z is the mean and the Gaussian, mean and the variance. And the way you learn that Q is by maximizing what we call the evidence lower bound. So you take that likelihood and the prior, that's nothing but the numerator, and you want to maximize this difference. And you will take a bunch of samples in order to compute that elbow, and you will have some objective that represents how can you achieve that, how you can find that posterior is what we call it. So the likelihood, it's composed of the same losses we saw earlier, the set distance loss and the transverse loss. And we want to make this loss go to 0. And the standard deviation, you can in fact learn that standard deviation at the same time during this Bayesian training. And your prior can be uninformed, like I said, it's unknown, or it could be from your deterministic training. So we use Bayesian learning techniques to account for these uncertainties. So we tried it on the inertial wheel pendulum. And what we did is we actually changed this wheel. We changed the wheel. We could put layers of wheels on that inertial wheel pendulum that I showed earlier. So we can put one ring. So we can change this ring, and we can increase it up to 4. And under these changes, how well does our controller perform? And the plot on the top right shows, so the Bayesian is the blue one. Again, this is accumulated cost, so we want to minimize that cost. So the blue is low. See that? So it accumulates less cost. And the orange one, not only does it accumulate a lot more cost, the band shows how much variance you experience due to the measurement uncertainties. And the deterministic is not robust against your measurement uncertainties. So we're gaining some serious advantages from the Bayesian training. So this is another variant of passivity-based control called interconnection damping assignment passivity-based control. And it looks quite similar in the sense that we still want to do that energy shaping form, but now we pick the Hg to be of this particular format. We want it to be the sum of the kinetic and the potential energy. But now we'll be learning this ND matrix and this VD function. And the reason why I want this quadratic form is, unlike NEURALPBC, I can actually say something about the H dot. I don't know if you noticed, but in NEURALPBC, I was not keeping track of what H dot looked like particularly. But if I pick it to be of this quadratic form, make this a neural network, make this a neural network, I can actually say, okay, H dot is quadratic. It still holds the passivity properties we had seen earlier. And the control synthesis is similar to how we had seen earlier. You want to make the port Hamiltonian, or the system after it has been transformed, to look to have some HD, and you can extract the controller accordingly. So the data-driven version of IDA-PBC is given as follows. You have some performance objective, and that is the partial differential equations we would have solved. We're merely trying to minimize the error. We're merely saying, okay, I don't know how to solve that PDE in closed form, but I can try to minimize the loss accumulated by that PDE. And we have the HD of the quadratic form picked, and the MD J2 comes from having to do that transformation. And we have these constraints. So the training process is similar to what we had seen earlier. So the difference here is that this HD, with a little bit of manipulation, you can make it just a function of your pose and not your velocities. So you can make it just a function of your configuration space. So IDA-PBC makes things a little more easier. So I sample my configuration space. If it's a pendulum, I sample a bunch of angles. And then I will evaluate the neural network that parameterizes the MD and the BD and the J2. And I can evaluate the controllers, just like how we did in passivity-based control earlier. But I can also construct the partial differential equations that I was supposed to solve, and I can instead minimize the loss created by these PDEs instead of solving them in a closed form. And then I can take the gradient of that loss with respect to the parameters, make that update, and repeat the process. And once the training is complete, you can test it on your IWP in this case. So this is a simulation result of the deterministic solution, right? So we learn point estimates over the parameters of MD and VD. And when you start it out and test it out from a bunch of initial states, you notice that it goes to the equilibrium we're interested in. And in this case, we shifted it such that zeroes up. It doesn't make a difference. And we were still able to inject the Bayesian training on top of it. So we also said, okay, we can learn the probability distributions over the parameters of BD and MD and J2 and do the same test, right? I'm changing my parameters and I'm seeing the performance index. And notice the orange one is the deterministic and the blue one is the Bayesian, and the Bayesian accumulates less cost. So this was also tested in an experiment. Like I said, we can remove those rings and we can replace them and run them. And it actually looks, there you go, it looks something like this. So this is the Bayesian training. And you change, whenever you change the wheel, you change the mass, you change the inertia, you change the center of mass. So you're changing a bunch of your parameters by just changing that ring. But despite that, we were able to make the Bayesian training work. So you do one Bayesian training under those uncertainties, you inject those uncertainties, and your controller seems to be robust against them. So where is this going? Well, the next thing is taking this one step further. We have interest in walking robots, and we have the simple system called the rimless wheel that represents a passive walking system. So if you want to make this rimless wheel go at a certain velocity, take this pendulum and you can actuate it, and that will shift your center of mass, which will roll the system down the hill, whether it's a slope or not. But the difference is you have contact. So we have these changes, these impacts and contacts that are suddenly changing our differential equations. So we no longer have a differential equation. We have measured differential equations. And we want to be able to learn a controller under these changes, right? Under these impacts and contacts. So that's a new, more interesting set of problems. We still have parameter uncertainties we need to deal with. But more importantly, when we take gradients now, we're no longer taking gradients through differential equations that we have seen earlier. The way you actually solve this system and the way you solve the discontinuities is through a linear complementarity problem, which is an optimization problem. So the next task is to take gradients through optimizations, which is possible if it's a convex optimization problem. And see its capabilities under uncertainties, such as, let's say you don't know the friction of your ground, you're on a slippery ground or you're on uneven terrain, can you still make your controller work? All right, this is everyone in the, not everyone, I guess, but this is the team from the Robot Control Laboratory that I would like to thank my advisor, Dr. Satichi, and now Dr. Wankusiri Shotiaku, one of our recent graduates who very much laid the groundwork for what I'm doing today. All right, thank you all.